There is a moment in science when the instrument meant to measure reality stops measuring it and starts rewriting it. This is that moment. What Google's quantum processor just did does not fit inside the existing vocabulary of physics. It does not extend the frontier. It does not push the boundary one step further. It appears to have walked straight through the boundary and kept going, and the people who built it are not entirely sure what is on the other side. Physics has always been humanity's most honest attempt to describe what the universe actually is, not what we want it to be, not what feels comforting or logical or beautiful, what it actually, demonstrably, measurably is. And for centuries, that project worked. Newton gave us mechanics. Maxwell gave us electromagnetism. Einstein gave us relativity. Quantum mechanics gave us the rules of the very small. Each framework was strange. Each one shattered assumptions. Each one replaced something comfortable with something true. But every breakthrough, no matter how radical, still played inside the same game. The rules changed, but the idea that rules existed did not. Until now. Because what Google's quantum chip just demonstrated does not merely change the rules. It raises the possibility that some of what we assumed were rules were never rules at all. They were limits, limits of classical computation, limits of classical observation, limits of classical reality. And a quantum machine operating at a scale and speed that breaks every prior benchmark may have just slipped outside those limits entirely. Not by accident, not as a glitch, but as a direct consequence of what quantum mechanics actually allows when you stop treating it carefully and let it run free. The result that triggered all of this is almost impossible to describe without the numbers sounding fictional. Google's Willow quantum chip completed a computation that would require a classical supercomputer longer than the age of the universe to finish. Not a faster classical computer. Not a better classical computer. Any classical computer that could ever be built. The task involved sampling random quantum circuits, a benchmark specifically designed to be computationally intractable for non-quantum systems. And Willow did it in under 5 minutes. 5 minutes against an astronomically large number of years. That is not an incremental improvement. That is a category break. That is the difference between a candle and the sun. But the raw speed is not what broke physics. Speed is engineering. What broke physics is the explanation for how that speed is possible. Because quantum computing does not work the way classical computing works. A classical system tests one path, then another, then another. Sequential, deterministic, grinding through possibility space one option at a time. A quantum system uses superposition and entanglement to explore multiple states simultaneously. That much is already taught in universities. That much is already accepted. But when the scale of that simultaneous exploration reaches the level Willow achieved, something deeply uncomfortable enters the conversation. The numbers do not add up in any universe containing only the matter and energy we can account for. The computation being performed requires more parallel processing than the observable universe contains resources to run. So, where is the computation actually happening? That question is not rhetorical. It is not philosophical decoration. It is a genuine, unresolved, scientifically serious question that quantum computing at this level forces into the open. And the answer that some physicists find most consistent with the mathematics is the one that sounds most like science fiction. The computation may be distributed. Across what exactly is the part that changes everything? Because the leading theoretical candidate is not a better processor. It is not a hidden corner of the existing universe. The leading theoretical candidate is other branches of reality itself. The many worlds interpretation of quantum mechanics, which has always been treated more as a philosophical framework than a physical claim, suddenly becomes relevant in a new and urgent way. If Willow's computation genuinely exceeds what one universe can process, and if the output is still correct and verifiable, then something outside this universe may be doing part of the work. Not metaphorically, literally. The many worlds interpretation was proposed by Hugh Everett in 1957 and spent decades on the margins of serious physics. The idea is that the universe does not collapse quantum possibilities into one outcome when measured. Instead, every possibility actually occurs, splitting into branching realities, each one real, each one containing observers who see their particular outcome as the only one. Most physicists found this difficult to accept, not because the math was wrong, but because the implications were so extreme. An infinite number of parallel universes branching with every quantum event felt like too high a price to pay for theoretical elegance. But Willow may be changing that calculation. Because if quantum processors at this scale genuinely require parallel realities to account for their computational power, then the many worlds interpretation is no longer just an interpretation. It is a testable, functional, engineering-grade description of how reality operates. And that is where physics breaks. Not gently, not politely. It breaks because the moment you accept that a machine built in a lab in California is offloading computation into parallel branches of reality to solve problems faster than the observable universe alone could ever manage, you are no longer doing physics in any sense that Newton, Maxwell, or even Einstein would recognize. You are doing something new, something without a clean name yet, something that sits at the intersection of computation, cosmology, and ontology, the study of what actually exists. The machine did not just solve a problem, it implicated the architecture of existence in its solution. There is something else happening inside Willow that goes beyond the raw computation speed, and it may be even more significant in the long run. The chip demonstrated a property called below-threshold error correction. In quantum systems, qubits are extraordinarily fragile. They interact with their environment, they decohere, they lose their quantum state before the computation is complete. Scaling up quantum processors has always meant scaling up error rates, which historically meant the advantage disappeared as the system grew larger. The prevailing assumption was that this was a fundamental obstacle, not an engineering problem, but a physics problem. Willow broke that assumption. As the system scaled up, the error rate went down. That is the opposite of what classical physics and prior quantum engineering both predicted. It is the opposite of what every previous quantum processor demonstrated, and it means something conceptually enormous. The universe apparently allows for quantum coherence to be maintained at scales previously thought impossible. The decoherence barrier was not a wall, it was a test. And Willow passed it. The implications of below-threshold error correction extend far beyond faster computers. If quantum systems can be scaled without collapsing under their own noise, then the theoretical ceiling on quantum computation essentially disappears. Every problem that was previously considered permanently intractable because of decoherence suddenly reopens. Simulating molecular behavior at quantum precision, a task that would unlock drug discovery, materials science, and energy technology simultaneously, becomes achievable. Modeling the quantum behavior of complex systems at scales approaching biological complexity becomes achievable. And most staggeringly, simulating the quantum conditions of early universe physics, the moments just after the Big Bang when everything was pure quantum foam, becomes achievable. We may be approaching the moment where a machine built by human hands can recreate, in silicon and superconducting loops, the conditions that produced stars, galaxies, and eventually the atoms inside the people asking these questions. But there is a darkness at the edge of that achievement. Because if quantum processors can simulate physical reality at quantum precision, the distance between simulation and reality begins to shrink in a way that is philosophically terrifying. Physics already tells us that the universe at its most fundamental level is quantum mechanical. If a quantum computer can reproduce quantum mechanical behavior at arbitrary scale, then the question of where the simulation ends and reality begins becomes genuinely unclear. Not as a thought experiment, as an engineering problem that someone is actively solving right now. The simulation hypothesis, long considered a topic for late-night philosophical speculation, suddenly arrives at the door of experimental physics with credentials it did not previously carry. Physicists like John Preskill, one of the most careful and respected voices in quantum computing, have noted that Willow's achievement represents a genuine milestone, not a marketing claim. The random circuit sampling benchmark was specifically chosen because it resists classical shortcutting. There is no clever algorithm that lets a classical machine fake the result. The quantum advantage is real, measurable, and verified. And while Preskill and others are careful to note that practical quantum advantage for real-world problems still requires more development, the trajectory is no longer ambiguous. The line between quantum supremacy as a demonstration and quantum supremacy as a tool has been crossed. The question is no longer whether quantum computers will outperform classical systems on problems that matter. The question is how soon. String theory and loop quantum gravity, two of the most serious attempts to unify quantum mechanics with general relativity, have both produced theoretical frameworks suggesting that space-time itself is not continuous. That, at the Planck scale, the smallest meaningful scale in physics, reality is granular, pixelated, discrete, not smooth, but composed of irreducible quantum units of space and time. If that is true, then the universe at its most fundamental level already operates like a computation, not metaphorically like a computation, structurally like a computation. Information theoretic physics, developed through the work of Jacob Bekenstein, Stephen Hawking, and later Leonard Susskind, goes further and suggests that the universe may store information on its boundaries rather than its interior, a principle called the holographic principle, which implies that the three-dimensional reality we inhabit may be a kind of projection from a two-dimensional informational surface. In that framework, reality is not just computation-like. Reality may be computation. And here is where Willow becomes something more than a faster processor. If the universe is fundamentally informational, and if quantum processors are the only machines capable of truly native interaction with quantum informational reality, then Willow is not just a computer. It is the first human-built system capable of operating in genuine sympathy with the deepest layer of physical existence. Every classical computer has always been a simulation of quantum reality, built on top of it, always separated from it by a layer of approximation. Willow removes that layer. It runs in the same register as the universe itself, and that changes what it means to compute. It changes what it means to know something. It may eventually change what it means to interact with reality at all. The researchers who built this machine are brilliant, careful, rigorous people. They are not making mystical claims. They are publishing peer-reviewed results and being precise about what has and has not been demonstrated. But the implications of what has been demonstrated are not fully within anyone's control. Physics does not stay where you put it. It spreads into every discipline, every framework, every assumption built on top of it. And what Willow demonstrated spreads far. If computation is happening in parallel realities, then reality is parallel. If error correction improves with scale, then coherence is a feature of the universe, not a fragile accident. If a machine can simulate quantum conditions of any physical system with sufficient accuracy, then the boundary between model and reality becomes negotiable. These are not small revisions. These are changes to the foundation. There is a version of history where Willow is remembered as one of those quiet announcements that did not seem important until decades later, when everyone looks back and realizes this was the moment. The moment a classical view of physics stopped being adequate. The moment computation moved from simulating reality to participating in it. The moment the observer became something more than a passive recorder of data and started to become something closer to an active element in the structure being observed. Physics has had those moments before. The day the photoelectric effect was explained. The day the double-slit experiment revealed that particles behave differently when watched. The day relativity removed absolute time from the universe. Each one felt like a revision at first. Each one turned out to be a revolution. This may be the next one. What Google's Willow chip ultimately confronts us with is not just a technical result. It is an identity question. Humanity has always defined itself partly by the limits of what it can know and what it can build. Physics was the language that described those limits most honestly. And now the tools we have built are beginning to exceed what the language can describe. Not because the tools are malfunctioning, because they are working exactly as the deepest physics predicts. A quantum processor powerful enough genuinely does touch parallel realities. A decoherence-resistant quantum system genuinely does suggest the universe prefers coherence at scale. A machine that can simulate quantum systems with precision genuinely does blur the line between model and matter. These are not anomalies. They are the logical destination of quantum mechanics followed honestly to its end. So here is what this moment actually is. It is the instant when the machine built to understand the universe began to resemble the universe it was built to understand, when the tool became something more than a tool, when the observer started to look less like a scientist standing outside the system and more like a new kind of participant in the system itself. Physics has not been broken in the sense of being proven wrong. It has been broken open, and what is inside is stranger, deeper, and more disturbing than anyone expected to find this soon. The rules are not gone, but the room that contained them just got infinitely larger. And somewhere in that larger room, parallel to this one, another version of this moment is also happening. Another observer, another machine, another question asked at the edge of what a civilization understands about itself. The question worth sitting with tonight is this: if a machine built by human hands is already doing work that requires more than one universe to explain, what does that mean for the humans who built it? Are we the species that cracked the architecture of reality, or are we the species that just discovered we never fully lived inside it to begin with? If that question changes the way you think about what physics is, what reality is, and what we are standing on the edge of right now, then stay with this. Because the next result from a machine this powerful will not just raise new questions. It may answer ones we were never supposed to be able to ask. Subscribe, think deeply, and do not let go of this feeling. It is the feeling of a species waking up to what it actually built.